Hi, welcome to the second lecture video from chapter 14. In this video, I'm going to talk about this line here. In the previous video, we talked about correlations and how to find the Pearson correlation and how to determine whether there's a pattern in the data that we're looking at and how strong of a pattern it is. So in this video, we're going to talk about how to actually produce the line of best fit, that is the line that best represents the pattern that we see in the data. In particular, that line is very useful because it makes a relationship that we're looking at easier to see. It also serves as a measure of the central tendency of the data, and it can be used for prediction. As you can see, at any given value of x, SAT scores, there is a predicted value of y. So the line is making a prediction of what value would be found um, at that particular x value. So obviously the data isn't falling exactly on that line. For some points it does, but for many they're either over or under the line. But you can also see how it's a like it seems to be like a pretty good representation. It's sort of running through the center of all the points. Um, so yeah, you can think of it as a measure of central tendency of sorts as well. So the equation itself, it's the formula for the equation that we're used to. So I learned it as y equals mx plus b, but here we're going to use y equals bx plus a. So b is a slope in this version of the formula, and a is a y-intercept. And these are constants, so the variables are y and x. So x is the input variable and y is the output variable. So what is regression? Regression is a method of finding that line that best fits the set of data. That best fitting line, the line of best fit, is actually defined by uh, being the line that minimizes what we call prediction errors. So y hat, this y with the caret over it, is the predicted value at a particular x position. So that's y hat is all the points that are on the line that you would see for the data. So y is obviously the what you actually got, right? So y is a data point, and y hat is the point on the line. So that distance, the difference between what was predicted and where the actual data point was, that's considered the error of prediction. So that's y minus y hat. So it's kind of like before we had seen deviances from a mean. So this is basically the same idea. And similarly, uh, in order to get rid of the negative numbers, we would square that, right? So this is kind of like a sum of squares. So this is the squared error. So the line that would minimize the squared error uh, when you're considering all of the points, that's what's considered the best line of fit. So for instance, you can see here we just have a regular line and our equation up here. So y hat. Y hat is all the points along this line, as I mentioned earlier. And the distance between any given point, that the data point, and where the line says that where that data point should have been, right, the prediction, that's the error. So you can see that every single point has an error. And you can think of the line of best fit. Um, you could tilt the slope of this line. So you can imagine it tilting in various ways, various degrees to fit the points differently, right? So when the points are close to being on a straight line, it's easier, but when they're spread out, it's kind of difficult to tell. But the line that's best fit would be the line that that reduces that distance for all the points together. And the way that we find this line would be by finding the slope. So the slope is found by taking the sum of products, which we calculated for correlation, and setting that over the sum of squares for the x variable. And the constant a is found by taking the mean of the y variable and subtracting the mean of the x variable times the slope that we get. So that's how you would construct this line, and then you could use that to make predictions. So we'll do a couple of practice problems in the next few videos.